Hello, this is Miss Moore, and today during chemistry we're going to start a series of lectures on the gas laws. And today we're going to talk about Charles' law. Today's essential question: what is the relationship between a temperature and volume of a gas? All right, let's start with a quick overview of the gas laws, a few terms you need to know. Okay, there are 4 variables that will affect the behavior of a gas. So quick definition on variables and constants. A variable are things that can change. Okay, and a constant are things that do not change. There are 4 different variables that will affect the behaviors of gases. We're going to go through all 4 variables right now, although today we're actually going to only focus on 2 of these. There's 3 things you need to know from this slide. You need to know the 4 variables, like pressure, temperature, volume, and moles. You need to know the abbreviations for those variables, which is P and T and V and N. And you need to know the units for each variable. All right, so the 4 variables are pressure, P, pressure exerted by the particles. The units can be ATM, mmHg, which stands for millimeters of mercury, PA, which stands for pascals, kPa, which stands for kilopascals, PSI, which stands for pounds per square inch, and torr. Then we've got temperature, represented by a capital T. And for the gas laws, the temperature needs to be in Kelvin. The units are capital K, Kelvin. And we'll talk about this one in just a moment. We'll practice it, but you do need to know this equality right here, that the temperature in Kelvin equals the temperature in Celsius plus 270 degrees Celsius. Okay, and we'll practice that in just a moment. Actually, why don't we practice it right now? Okay, so if I had something like 82 degrees Celsius, and I wanted to know what it was in Kelvin. Well, we have temperature in Kelvin equals temperature in degrees Celsius plus 273. So to calculate temperature in Kelvin, it would be temperature Kelvin equals 82 degrees Celsius plus 273. And that gives us a Kelvin temperature of 355. Now for Kelvin, we don't usually use a degree symbol. It's just 355 Kelvin. Okay, the other way you could do this is if I gave you a temperature in Kelvin, like 400 Kelvin, and I wanted to know what that equals in degrees Celsius. Well, we'd use the same formula, right? Temperature in Kelvin equals temperature in degrees Celsius plus 273. So we would have 400 K equals temperature in degrees Celsius plus 273. Now, to solve for temperature in degrees Celsius, we would just subtract 273 from both sides. And that would give us a temperature of 127 degrees Celsius. Okay, so that's how you convert back and forth from Kelvin to Celsius. You do need to know this formula. Okay, so we've got pressure, we've got temperature. The next variable is volume, represented by a capital V. And it's the volume occupied by the particles, or the space the particles take up. Volume can be anything liters. So it could be liters, milliliters, centiliters, milliliters, kiloliters, any kind of liters. And anything cubed. Feet cubed, centimeters cubed, millimeters cubed, decameters cubed, meters cubed, anything cubed. Okay. So of these 4 variables, we're going to spend the most time working with pressure, temperature, and volume. The last variable is number of moles. It's represented by an N, not by an M, because capital M is molarity, small m is meters. So we use small n representing number of moles. We will not be talking about that until later. So of the four, we'll be spending most time with pressure, temperature, and volume. And today we'll be dealing with temperature and volume. Okay, so those are the four variables of the gases. Once again, you need to know the names, pressure, temperature, volume, and moles. You need to know the abbreviations P, T, V, and N, and you need to be familiar with the units, okay? Okay, the gas laws allow us to predict behavior of gases under certain conditions. And there are going to be 4 laws we're going to talk about, actually 5, but 4 of the 5 are all going to use the same equation. This guy right here. P1 V1 over T1 equals P2 V2 over T2. So that's that's pressure 1 times volume 1 divided by temperature 1 equals pressure 2 times volume 2 divided by temperature 2. And the 1 stand for original and 2 stand for the changed or the new. Okay, so you need to know this equation, although we're going to use it so much it won't be a problem. P1 V1 over T1 equals P2 V2 over T2. Okay, finally, we're done with the background information. Let's talk about Charles' law. Heating a gas will make it expand. Why? Because kinetic energy. Gas molecules move faster when heat energy is adding to them, causing them to strike with more force against the walls of their container, which leads to an increased volume. If you think about if they were inside a balloon, if you took a balloon and stuck it in your hot car in August, the balloon's going to get bigger, might even pop, right? It's because those gas molecules are moving faster and faster and faster, hitting the size of the balloon harder, causing the size to get larger, okay? Conversely, the volume of a gas decreases when the gas is cooled, because as you cool those particles down, they move slower. They're not hitting the sides of the container as hard, in this case a balloon. It's going to make the volume decrease. So if you want to make a balloon smaller, at least for a moment, you can stick it in the fridge, right? Those particles will start moving slower. It'll decrease the size of the balloon. But as soon as you bring it back to room temperature, it'll go back. The molecules will speed up, go back to its original size. You put it outside where it's really hot, they'll speed up more, hit the walls of the container harder, the balloon, make it even larger. So here's Charles' law. The volume change of a gas caused by a change in temperature at constant pressure, that's important, Charles is ignoring pressure, is expressed as Charles's law. So here's his actual law. The volume of a gas is directly proportional to the temperature on the Kelvin scale at constant pressure. So what does directly proportional mean? This will be a test question. Directly proportional means that the temperature and volume change in the same direction. They both increase or they both decrease. So in this case, if we increase the temperature, we're going to increase the molecule movement, which is going to lead to an increase in volume. If I decrease the temperature, I'm decreasing the molecule movement, which is going to lead to a decrease in volume. Okay, so they go in the same direction. They both increase, they both decrease. And here is a little graph showing you what a directly proportional relationship would look like. As you increase temperature, you increase volume. As you increase volume, you increase temperature. So that's the basics of Charles' law. Now remember, we're holding pressure constant. Charles is only interested in is only interested in volume and temperature. So when we're making a prediction about gas behavior using Charles's law, we're still going to use the formula P1 V1 over T1 equals P2 V2 over T2. However, we get to ignore pressure. We just ignore it. It's just not there. So we're going to just use V1 over T1 equals V2 over T2. And now it's time for a practice problem. All right, so the way I do these problems is I make a list of all the variables. It just helps me, reduces the stupid mistake factor. So we have P1, V1, and T1 equals, and P2, V2, and T2 equals. Read through the story and let's see if we can figure out who's who. So we've got a balloon inflated in a room at 50 degrees Celsius, has a volume of 7 liters. Well, to me it sounds like at 50 degrees Celsius we have a volume of 7 liters. Those go together. The balloon is then heated to a temperature of 69 degrees Celsius. What is the new volume? So those are going to be our X's. All right, so let's fill that in. We have got a T1, a temperature of 50 degrees Celsius. Did that wrong, 50 degrees Celsius. And we have a volume 1 of 7 liters. We have a temperature 2 of 69 degrees Celsius and a volume 2 of X. And we're going to ignore the P's. Now, there's one issue here. If you look, we have degrees Celsius. If you remember, temperature for gas laws is in kelvins. We have to use the units Kelvin, which means we need to use this equation. Temperature in Kelvin equals temperature in Celsius plus 273. So for T1, we're going to have temperature in Kelvin equals 50.0 plus 273. Giving us a temperature of 323 Kelvin. All right, we need to do the same thing for this one. We're going to have temperature in Kelvin equals 69 degrees Celsius plus 273. And that gives us a Kelvin temperature of 342 Kelvin. Okay, so now that we have our list of variables, we just need to fill them into our formula P1 V1 over T1 equals P2 V2 over T2. So we don't have a pressure, so we get to ignore it. So we have V1 of 7 liters over T1, which is 323 K, equals pressure 2, we ignore. So we have V2, which is X, over T2, which is 342 K. Okay, let me erase this stuff up here so we have a little bit more room to work. So now to solve a problem where we have two fractions with an equal sign in between, we cross multiply. So we're going to have 7.00 liters times 342K equals 323K times X. Now let's go ahead and multiply. And when I did that, I hope some of you are checking me, 2,394 liters Kelvin equals 323K X. Now, how do we get the X by itself? We'll divide by both sides by 323K. So our K's cancel out, we're left with liters, and when we divide, we get 7.41176 and so forth liters. So our final answer is 7.41 liters. Now we can check really quickly. Remember, Charles' law says that volume and temperature are directly proportional, which means if one goes up, the other one goes up, and if one goes down, the other one goes down. So we're going from 50 degrees Celsius to 69. So temperature is increasing, which means volume should also increase. And I started out with 7 liters and I'm at 7.41 liters, so we probably did it right. Okay, let's do a second practice problem. This time, however, why don't you hit pause, try to do it without my help, then hit play and see how you did. Okay, I'm going to start by making a list of my variables, and I've got P1, V1 and T1, and P2, V2, and T2. All right, so I have a balloon that's inflated in a room at 22 degrees Celsius, and that thing has a volume of 62.3 liters. That all goes together. And then at what temperature would the balloon have at a volume of 73.9 liters? All right, so my T1 is going to be 22 degrees Celsius, except that I need to change that to Kelvin, so that gives me a 295 in Kelvin. Let's see, my V1 is 62.3 liters. My T2 I don't know, and my V2 is 73.9 liters. All right, so from here I'm going to fill things in to the formula P1 V1 over T1 equals P2 V2 over T2. All right, so I don't need to worry about the P's because I don't have any of those. So my V1 is 62.3 liters, and my T1 is 295 K. My V2 is 73.9 liters, and I don't know T2. All right, I'm going to cross multiply, giving me 62.3 liters times X equals 295 K times 73 point, oh, that's not going to fit. All right, let's try this again. It's giving me 62.3 liters times X equals 295 K times 73.9 liters. All right, so when we multiply, I end up with 62.3 liters X equals 21800.5 Kelvin liters. There's a liters there. All right, to get the X by itself, we'll divide both sides by 62.3 liters, giving us 349.9277 and so forth Kelvin. Let's double check ourselves. Our temperature originally it went from 22 to, let's see, that's temperature in Celsius. Here's Kelvin. 295 to 350, so our temperature increased. Did our volume also increase? Original was 62, second is 73, so we probably did it right. All right, folks, that's it for today. Have a good one.